We will now discuss quadratic programming for constraint optimization. In this particular lecture, we will understand how the quadratic programming can be used to solve the constraint optimization problem, and the procedure which we will understand in quadratic programming. We will use that procedure for making a method called sequential quadratic programming. In short, this is called as SQP. In quadratic programming, so in short, it is saying it is referring as QP. The objective function is approximated with quadratic function, and the constraints are approximated linearly, say using Taylor series expansion. If we are going to write KKT conditions for the quadratic programming in which our objective function is quadratic and the constraints are linear, then all KKT conditions will become the linear functions of variable. Since all these conditions are linear, we can use the LP solution methodology. For example, we can use Simplex method to solve those conditions and find a solution or a solution which is satisfying all KKT conditions. As we remember, the KKT necessity and sufficient theorem says that a function, if a quadratic problem with a positive semi-definite matrix is a convex problem. So as and when we are going to get a convex problem, the KKT condition will give us a point and that will become the minimum or the solution of that convex problem. So this theorem we have understood. So we are going to use this concept in quadratic programming in the following slides. Suppose the constraint problem is given in the format of the function fx, inequality constraints, equality constraints, and variable bounds. So as we remember that if we are going to, when we are going to make the KKT conditions in that case, and after that we are going to solve using simplex method. So the resulting LPP for all the variables, those variables should be non-negative, meaning that x should be greater than equals to 0. In order to do that, we have to do a one transformation which you can see as xi prime is equals to xi minus xi lower. This transformation will make sure that we are going to get a non-negativity condition, that is xi prime greater than equal to 0. A generalized quadratic function or a problem can be written as, so this standard term we have written earlier as well. We can see that we want to minimize our objective function, which is a quadratic function, that can be written as f plus e transpose x prime plus half x prime transpose hx. So we remember that H is a matrix. Then this particular problem is subjected to inequality constraint, equality constraint, and this is the non-negative condition which we found in the previous slide. For a given NLP, the quadratic problem at a current point, say x prime, can be written as. So as we know that if suppose we are going to get a point, say x prime t, at that point we can use Taylor series expansion, and the function f can be approximated in a quadratic form using Taylor series expansion up to 2 terms. So this is the standard term or the Taylor series expansion we are using. Since it is quadratic, so we are representing as minimizing the q. Similarly, the inequality constraint Gj and equality constraint Hk, both of them are written up to one first term in the Taylor series expansion. So that's why it is a linear equation in terms of x prime. So here we have the objective function as quadratic and the constraints are linear. And after transformation xi prime says that it should be greater than equals to 0, and there is an upper bound as well. Now let us write the objective function and constraint in symbolic form. What we mean by symbolic form? So let us identify what is capital F, E, H, A, B, C, and a D. So these are the symbolic forms which we can write a quadratic programming problem. Now here, this upper bound, which is x prime, is smaller than, this should be smaller than and equals to xi upper minus xi lower. Now we are considering as an inequality constraint. So this particular constraint we can convert in the form of j of x greater than equals to 0. This means that this x prime will go on the right hand side, will be negative. So this particular constraint is written as greater than equals to 0. Now let us write the constraint as represented in the form of x prime, a of x prime greater than equals to b. So in this case, what is a? A will become gradient of a g1 x prime t, the transpose. So this is going to be a one vector. Similarly, gradient of a g2, similarly gradient of a gj at x prime t. So this is a given point to us. And as we have included the upper bounds as constraint for our problem, then we are writing minus I1 to minus IN. So how many, what is the size of A? So the size of A will become, so we have J inequality constraint plus we have variable bound, so that they are n number of variable. So we are going to have J plus n as number of rows cross, and there will be n, which will be the number of columns. Similarly, we can find B in terms of G1 to Gj. So this term is written as G1 x prime t plus gradient of a G1 x prime t transpose x prime t. So this we are going to do for all Gj. And then you remember that since we are using the upper bounds as a constraint, so we have x1 upper minus x1 lower, and this is happening for all the variable. Now the point is, what is I1? So if you take I, so it's going to be a zero vector. Only at the ith element, this is 1. So you can assume that it is a one of the column of the identity matrix, in which if we say I, this means at the ith place it is 1 and rest of the elements are 0. Now you may be wondering how we are getting A and a B. So if I go back, so as you remember, we have written our NLP in this particular form. If we simplify all these equations and fit into this form, which is given on the top as a quadratic problem, then those who are multiple with the x prime will become a part of A matrix. So therefore, you can see with inequality and equality constraint. So this x and x prime, that will be the part of gradient of a G and gradient of H. So that way we have identified A and a B. Here you have to do handwork. You perform some hand calculation, then it will be easier to have this kind of a representation. Similarly, if we follow the same procedure to find the symbolic representation for equality constraint, so the capital C will become gradient of H1 x prime t. Similarly, this will be happening for all k. So this k should be a capital K. Now this particular matrix will become size of k. So the number of constraint, equality constraint into the number of variable. Similarly, we can find the small d by simplifying our equations. Now comes the objective function, because we have identified AB and CD. So all symbolic representation for constraints are over. Now we are going to write the objective function. Now the objective function is written in terms of capital F, small e, and capital H. So here in this particular form, since F is a vector of a constant, so every constant term will be coming here. So the capital F is function value at x prime t, gradient of the function at x prime and then multiply by x prime t. And similarly, the third term. What is E? Suppose we are ignoring the constant term. So this E will come as a gradient of f of x prime t minus h of x prime t, x prime t. Now what is h? H is our Hessian matrix of the quadratic function, quadratic approximation of f with respect to the point which is given as x prime t. Now if we are going to write the KKT condition for a quadratic equation, so this quadratic equation, so the quadratic programming problem which is given on the top, I suggest you to do your hand calculation, write the KKT condition. Those KKT conditions should match here. So we have equation 2 that comes from the optimality condition. Then we have the 2 constraint. Equation number 5 is the complementary slackness, and 6 is the condition. 6 are the condition on the variable and the Lagrangian multiplier. Now here the Lagrangian multiplier mu is of the size of j plus n. Omega is the size of equality constraint. Nu is the size of number of variable. So how this nu is coming? Nu is coming from the constraints that are made using the upper and lower bound. Now suppose if we are going to find a solution, so the solution which is satisfying all the equations will become the solution for the quadratic problem. Now, as I have mentioned here, solution to the above KKT conditions can be found using Simplex search method for LPP because all constraints are linear. Now let us, since we have to solve these KKT conditions, let us add those artificial and slack variable. So I'm going back again. So equation number 2 has an equality constraint. So we know that the artificial variable will be added. Equation 3 has a greater than type. This means we are subtracting the slack variable as well as adding one artificial variable. Similarly here, this is an equality constraint. So let us see how we are doing it. So here, the first one, you can see that we have added a artificial variable or set of artificial variable as p in our equation number 1. Then in equation number 2, we subtracted the slack variable, then added the another artificial variable. And equation number 3, where we have the equality constraint, we are also adding the artificial variable. So P, Q and R are our artificial variable and S is a slack variable. So now you know that since we have converted every form into the equality constraint, now we have to solve it. For solving it, what is the objective function? Because since all of them are KKT condition, here the objective function, as we remember, two-phase method. So in the phase 1, our objective is we have to remove all the artificial variable. So therefore, if we minimize the all artificial variable, as you can see at the bottom, so these artificial variable, if we minimize, so when they will become non-basic variable, so they are all 0, meaning that the solution which we are going to get becomes the feasible solution for the given problem. Now we don't have any other objective to solve the given problem. We have just one objective, which is we are going to minimize all artificial variable. Now we remember that for solving a problem, we have the algorithm, the simplex method algorithm for maximization function. So let us convert it. So the resulting problem for a maximization, so we are just multiplying with the -1. We have all the constraints as we have written in the last slide. And then we have the variables which are greater than 0 and omega should be free. Now here there are certain addition terms. So these are the complementary slackness conditions where mu I Si should be equals to 0 and mu I Xi prime should be equals to 0. So these are the following conditions we have to met. So when these two conditions are adding, so along with that we are solving we will be solving the given LP using simplex search method, but we have to perform some condition with the simplex method. So that I will explain you now. So the simplex method which we are using for solving the given LPP is called conditioned simplex LLP. Now here, what is conditioned here? Suppose xk is a current basic variable, and we remember that we find delta fq to find which non-basic variable should come into our table. Suppose mu k is going to enter. Now, as we know, this xk and a mu k will become this complementary slackness condition, such as xk mu k equals to 0. So in this case, we are not going to select mu k. Why? Because sk is already a part of a basic solution. So mu k is already 0. So this condition of complementary selectness is already satisfied. So what we are going to do is will be looking for the next highest number of delta fq value, so that of the non-basic variable. So the chosen non-basic variable, its complementary variable is not basic, we will choose it. Otherwise, we will go to the third one. So we have to just make sure that looking at these two additional condition as mu I si equals to 0, mu I xi prime equals to 0. So if any of them, either mu I or si can become feasible, mu I or si will become basic. So other should be non-basic. Similarly, mu I or xi prime one of them should be basic, other should be non-basic, so that these two conditions will remain satisfied. So that is a simple rule which we have to make it while we are choosing a non-basic variable that is going to enter into the table. And that's why this simplex method is called conditioned simplex method. Let us take an example now. Here we want to minimize a function. This is quadratic in nature, and we have two constraints, x1 and x plus 1 x2 smaller than 2, and 2x2 minus x1 equals to 0. So we have a smaller than type and equality constraints. It's already a quadratic function and two linear constraints. So we can write the symbolic form or we can write directly. So we are following the symbolic form here. So looking at this equation, we can find h, which is the Hessian of the function fx. Similarly, I can find e, a, c, b, and a d. Once we have written everything in a symbolic form, we can put in our resulting LP. So as you remember, we want to minimize all the artificial variable. So let me go back. Here in G1, we don't need any artificial variable. We have to just one slack variable. But in G2, we have to add a artificial variable. Similarly, the KKT condition corresponding to the optimality, which will be gradient of fx, we will be needing two artificial variable here. So that's why you can see P1 and a P2 are the artificial variable. So we have written in a standard form, which we have understood in the previous slide. Then the constraint 1, constraint 2, and then we have all the variables, and then the omega is free. We have the following slackness condition with us. Now this is the LLP, and this we can solve using condition simplex method. Since we already know how the simplex method works, so I'm showing you the direct result that the simplex method generate the result as 1.33, 0.67, and the function value is minus 4.44. Let us look at the graphically this example. So you remember that there is a one constraint G1. The another constraint is equality constraint. So in our case, this particular line is the feasible region and the optima is lying here. And this is the same optima we got it using sequential quadratic programming. Now in the previous section, what we understood is that if we have our objective function quadratic and the linear constraint, by making a KKT condition and solving the simplex method for minimizing all artificial variable, we can get a solution for the LLP, and that solution is a KKT point. Since it's a quadratic, if the function is if the problem is convex function, the KKT point itself is the optimum solution for the given problem. But as of now, as we understood that the problem can be NLP, means it can have non-linear function in as objective function as well as constraints. So what we are going to do is we will be converting this NLP into the quadratic form using Taylor series function at a given point, and then we will apply this quadratic programming procedure in a sequence. And therefore, the method that will come is called sequential quadratic programming. SQP is a very famous method, and it has been used with many of the commercial software. For example, it is already a part of a MATLAB. So you can solve your constraint optimization problem using SQP in MATLAB. Similarly, there are other commercial software. Since SQP is a very famous algorithm or a method to solve nonlinear programming, so we will understand how it works. Now in SQP, first we start with the iteration t equals to 0. We will be starting with the initial points x0 and the termination condition e1 and e2. Step 2, we are going to transform first. So we have a given xt, we are going to transform in x prime t. So you may be remembering that we have to perform this x prime t for a nonlinear programming problem, NLP. Now we are converting the objective function as well as the equality and inequality constraint into the quadratic and linear approximation using Taylor series expansion at x prime t. Once we have done it, now we are going to get an LLP and we will be solving using condition simplex method. When we are solving it, suppose the solution of the LLP is y prime t. So in step 4, we look for the termination condition. Here we check two conditions. Y prime t minus x prime t is smaller than epsilon, meaning that if both the solutions are very close, because we are calculating numerically, so if they are very close, we should terminate, or the function value are very close, then we should also terminate. In both the cases, when we are terminating, we are reporting the result as a y prime t. Else, we will increase the counter t by 1 and go to the step 2. Now in this particular chapter, the objective was to understand how the quadratic programming works, and this quadratic programming can be extended to SQP. So we will not be doing any hand calculation for SQP right now, but if we can do hand calculation for QP, we can very well understand how SQP works. So I believe that this SQP will be useful, and as and when it will be needed by you to use in your report or in your work, or maybe in some kind of an interview, you will be able to explain how SQP works. So with this, I'm concluding this lecture on quadratic programming. It's a short lecture, but you need hand practice to write all the approximations, quadratic and linear approximation, and then fitting everything into the symbolic form that need practice. So therefore, I request everyone, you should do hand calculations properly so that you can understand each and every term. So that will help you to understand the whole programming, whole method, the quadratic programming, as well as sequential quadratic programming. So I'm concluding this lecture.